Imagine standing at the edge of an infinite ocean where the horizon stretches endlessly before you and the waves crash quietly at your feet. You feel the wind against your face, and a deep sense of wonder fills you as you gaze out into the vast expanse. But despite the awe you feel, you can never see where it ends, only the endless promise of what lies beyond. This is the experience we face when we contemplate the boundary of our solar system. Just as the ocean stretches to the farthest horizon, our solar system reaches out into the cosmos. But where does it end? How far does it truly extend? What lies beyond the familiar worlds we know? These questions, seemingly simple, yet profoundly deep, invite us into the heart of the mystery of space itself. Our solar system, despite its immense size, is not infinite. At its outermost edge lies the Oort Cloud, a vast, almost mythical region filled with icy bodies that remain from the early days of our solar system's formation. Some scientists speculate that this distant region contains the remnants of comets, debris from the time when the planets were first born. The Oort Cloud is thought to extend about 1 light year from the Sun, making it a massive and distant part of our cosmic neighborhood. But even this distant cloud raises questions that go beyond simple astronomical observations. Is the Oort Cloud truly the boundary of our solar system? Or could there be something even more elusive, perhaps yet undiscovered, lurking just beyond its reach? Beyond the Oort Cloud, we enter interstellar space, where the influence of the Sun begins to fade and the stars of other solar systems begin to dominate the night sky. This transition from the familiar to the unknown forces us to reconsider what it means to be a part of our solar system and to question how we define its edges. The Oort Cloud could be considered the frontier of our solar system, a boundary that stretches outward, marking the farthest point of influence the Sun has over the icy bodies scattered within it. This boundary, nearly 1 light year away, seems like a definitive edge. Yet, just beyond it, lies the vast, uncharted, interstellar space. And what if this space is not as empty as it appears? Could there be other solar systems, each with its own star and planets, scattered beyond our reach? What if there are ancient civilizations, cosmic phenomena, or mysteries that we can only dream of? The idea that our solar system could blend seamlessly into the infinite expanse of space without a clear division challenges our perception of what it means to be part of something much greater. It forces us to reflect on our place in the universe, not just as inhabitants of a single star's orbit, but as small travelers in a cosmos that is far more complex than we can imagine. But what is the real purpose of this boundary? Is it merely a physical divider, or is it more symbolic of something much greater, something we might not yet fully comprehend? To answer this, we must look deeper into the forces that govern the universe, forces that are often invisible and beyond our understanding, yet shape the very fabric of reality itself. If the solar system were a grand ballroom, the planets would be the dancers, gracefully swirling around a central star, each with their own rhythm and movement. But in this cosmic waltz, there is one unseen partner guiding the dance: gravity. This invisible force is what keeps the planets in their orbits, ensuring they don't drift away into the vast emptiness of space. It is the silent conductor, ensuring that the planets move in harmony, and that everything in the solar system stays in its place. But what is it that keeps these celestial bodies from colliding or flying off into space? What unseen force governs this majestic, orderly movement? Gravity is the force that pulls objects toward one another, and it is the fundamental force that shapes the structure of our solar system. Every planet, moon, asteroid, and comet is held in place by gravity. The Sun's immense gravitational pull keeps all the planets in their orbits, preventing them from drifting off into the void. Without gravity, our solar system would be nothing more than a scattered collection of bodies, each moving aimlessly through space. But gravity isn't only at work between the Sun and the planets. It also governs the interactions between the planets themselves. Take Jupiter, for example, the largest planet in our solar system. Its massive gravitational field influences not only its own moons but also the orbits of nearby asteroids. It acts like a cosmic shield, sometimes redirecting asteroids that could otherwise impact Earth, protecting our planet from potential disasters. In this way, gravity not only keeps everything in orbit, but also plays a role in safeguarding life on Earth. While gravity is a well-understood force, its full nature still holds many mysteries. On the scale of the solar system, we observe the familiar effects: planets orbiting the Sun, moons orbiting their planets, and comets tracing their elliptical paths. But when we zoom out to a galactic scale, gravity behaves in ways that are not fully understood. For instance, the galaxies themselves are held together by gravity, yet they spin in such a way that the gravity we observe doesn't seem to be enough to explain the motions of stars within them. This is where the concept of dark matter comes in, an invisible form of matter that doesn't emit light but exerts a gravitational influence on visible matter. Could dark matter be the key to understanding the larger scale effects of gravity? Does gravity truly explain everything, or is there more to discover about the fundamental forces at work in the universe? As we ponder the nature of gravity, we are left with even deeper questions. What lies beyond our understanding of gravity's reach? Are there cosmic forces influencing our solar system from afar, forces we have yet to uncover? To answer this, we need to explore some of the more mysterious phenomena of the universe, beginning with the strange and elusive cosmic anomalies that challenge our perceptions of reality. Imagine a vast, invisible ocean that surrounds every galaxy, every star, and even every planet in the universe. You cannot see it, touch it, or directly observe it with any of our current instruments. Yet, it's there, affecting everything in ways we can't quite explain. This invisible substance is called dark matter, and it makes up about 27% of the universe's total mass. Although it remains elusive, its presence is undeniable, as it exerts a gravitational pull that shapes the very structure of the universe. The question we must grapple with is, what exactly is dark matter, and why can't we detect it, even though it clearly plays such a crucial role in the cosmos? Dark matter is an enigma in the field of astrophysics. It cannot be seen, as it neither emits, absorbs, nor reflects light, making it completely invisible to all forms of electromagnetic radiation, such as visible light or radio waves. Yet astronomers know it exists because of its gravitational effects on visible matter. For instance, the way galaxies rotate cannot be explained solely by the gravity of the visible stars and gas that they contain. If only the visible matter were at play, galaxies would spin apart. However, dark matter provides the extra gravitational pull needed to hold galaxies together. It's as if there is an unseen force binding galaxies and other cosmic structures, preventing them from unraveling. Similarly, dark matter affects the motion of galaxy clusters and plays a role in the large-scale structure of the universe. In short, dark matter acts as a cosmic glue, holding the universe together in ways that we cannot directly observe but can only infer from its effects on the visible world. The implications of dark matter are profound. If dark matter makes up a significant portion of the universe, what else does it influence that we cannot yet detect? Could dark matter be more than just a passive player, shaping galaxies and clusters? Could it be the key to unlocking new forms of energy or even other dimensions? Some scientists theorize that dark matter might interact with itself in ways we don't yet understand, and that studying its properties could open the door to entirely new realms of physics. The fact that we cannot detect dark matter directly suggests that there might be entire realms of reality that exist beyond our current scientific understanding. Perhaps there are other types of matter, forces, or phenomena that we are only beginning to glimpse, and dark matter is just the first hint of what lies beyond the limits of our instruments and comprehension. As we explore the mysteries of dark matter, we are left to wonder what other forces in the universe we cannot yet perceive. Could there be other strange and hidden forces beyond gravity and dark matter that shape the cosmos? To begin answering this question, we must venture into the realm of cosmic anomalies. where strange phenomena defy our understanding of space, time, and reality itself. What if the universe was not just an endless expanse of stars, galaxies, and empty space, but instead a vast, intricate web of connections links that could allow us to travel across vast distances in an instant? Picture this: a tunnel stretching through the fabric of space-time, connecting two distant points in the universe. You could step into one end and emerge millions of light years away, without having to cross the intervening space. This idea, known as a wormhole, has captivated both scientists and science fiction enthusiasts alike. But is it just a theoretical curiosity? Or could wormholes be real, hidden pathways that could one day revolutionize our understanding of space and time? Wormholes are a theoretical prediction of Einstein's general theory of relativity. According to this theory, space and time are not fixed entities, but are instead flexible, bending and stretching under the influence of gravity. This creates the possibility that, rather than simply traveling in a straight line through space, it might be possible to create a shortcut between two distant points in the universe. A wormhole is often described as a tunnel with two ends, each located in separate regions of space-time. These ends might be in different places or even in different times. If such structures existed, they would essentially serve as shortcuts tunnels that could connect two separate points in the universe, allowing for instantaneous travel between them. However, while wormholes are mathematically possible according to the laws of general relativity, we have yet to observe any direct evidence of them in the cosmos. Theoretically, they could exist in the fabric of space-time, but whether they are stable or traversable by humans is still up for debate. The implications of wormholes are nothing short of extraordinary. If they existed and were stable enough to travel through, wormholes could effectively allow us to bypass the vast distances between stars and galaxies. Space travel, which currently takes years, decades, or even centuries, could be accomplished in an instant, opening up the entire universe to exploration. Beyond travel, wormholes might even offer a window into other dimensions or parallel universes, a concept that challenges the very nature of reality as we know it. Yet, this opens up a range of paradoxes and questions. For instance, if wormholes could allow us to travel instantaneously through time and space, could they also allow for time travel? Would traveling through a wormhole back in time create a paradox, allowing us to change the past and alter the course of history? These questions show just how deeply wormholes challenge our current understanding of physics and the structure of reality. While the concept of wormholes presents an exciting avenue for potential space travel and even time manipulation, it also brings us to the limits of our current knowledge. What lies beyond our understanding of space and time might be even stranger than we can imagine. To further explore these mysteries, we need to consider the very nature of the universe itself and the observable limits of our cosmic reach. What happens when we look beyond the boundaries of what we can see into the vastness of the unknown? The universe is vast, immeasurably so. When we look up at the night sky, we see a tiny fraction of what is truly out there. Our eyes can only take in the stars within our line of sight, and even the most powerful telescopes can only observe so much. But what if everything we see is only a fraction of what actually exists? The concept of the observable universe helps us understand the limits of our vision and forces us to confront the staggering reality that there is so much more beyond our reach. So, what lies beyond this vast yet finite boundary? How can we even begin to comprehend the size and scale of the universe if we can never truly observe it all? The observable universe is defined as the portion of the universe that we can see, or more accurately, the part of the universe from which light has had enough time to reach us since the beginning of the universe. Given that the universe is about 13.8 billion years old, the observable universe has a radius of about 46.5 billion light-years. This seems like an enormous distance, and it is, but it's important to remember that what we observe is not just the present, but the light from the past. When we observe the furthest galaxies, we are seeing them as they were billions of years ago. The limit to what we can observe is not based on distance alone. It's also constrained by the speed of light and the time it takes for light to travel across the vastness of space. While we can detect galaxies, stars, and other cosmic objects far beyond our immediate reach, we cannot see beyond a certain point the cosmic horizon, beyond which light from more distant objects has not yet had time to reach us. The idea of the observable universe raises profound questions about the nature of the cosmos. If the observable universe has limits, then what lies beyond those limits? Is the universe infinite, with countless galaxies stretching far beyond the furthest we can see? Or could it be that the universe has an edge, a boundary beyond which there is nothing? Some theories suggest that the universe might continue indefinitely, with new regions of space that we will never be able to access due to the expansion of space itself. As the universe continues to expand, more and more of it will be forever out of reach. If the universe is expanding faster than the speed of light, certain galaxies and regions of space will be receding from us faster than we can observe them, making it impossible to ever detect them. Moreover, what is it that lies beyond the observable universe? Could there be regions of space where the laws of physics we know don't apply, or where new, unknown forces and entities exist? The unknown realms of the universe challenge us to question our very understanding of space and time. Are we truly on the edge of understanding? Or are we merely scratching the surface of a far greater cosmic reality? As we confront the limits of our observation, it becomes clear that we are just beginning to understand the true nature of the universe. But these limits don't only pertain to what we can see, they also extend to the forces that govern the universe itself. To deepen our understanding, we must explore the theory of cosmic inflation, which offers insights into the universe's earliest moments and the potential structure of the cosmos beyond the observable limits. Imagine a balloon, tiny and compressed, with every part of it pressed together. Now, picture it expanding, rapidly, at an almost incomprehensible rate. In just a fraction of a second, the balloon is no longer small, but vast, stretching to a size that seems impossible. This concept, though strange, is key to understanding how our universe began. Cosmic inflation is the idea that, in the earliest moments after the Big Bang, the universe expanded at an exponentially rapid rate, far faster than the speed of light. It is a theory that not only reshapes our understanding of the universe's beginning, but also offers answers to some of the most perplexing questions in cosmology. But how could the universe expand faster than the speed of light? And what does that mean for our understanding of space and time? The theory of cosmic inflation was proposed by physicist Alan Guth in the 1980s to address certain puzzles left by the Big Bang theory. According to inflation, the universe underwent an incredibly rapid expansion, growing by a factor of 10 to the 26, a number so large it's almost impossible to grasp, in a fraction of a second, just 10 to 32 seconds after the Big Bang. This expansion, however, was not like the spreading of an explosion or the stretching of matter. Instead, it was a stretching of space itself. During inflation, space-time itself expanded so quickly that it caused regions of space that were once in close proximity to move farther apart, faster than the speed of light. This expansion explains why the universe appears so homogeneous and isotropic, meaning it looks the same in all directions, even though the universe is vast. Without inflation, the universe would have looked much more chaotic, with irregularities and imbalances that we don't observe today. Cosmic inflation also provides a potential explanation for some of the larger-scale structures of the universe. It suggests that tiny quantum fluctuations in the fabric of spacetime during inflation were stretched to enormous scales. These fluctuations eventually became the seeds for the formation of galaxies, stars, and other structures we observe today. Essentially, inflation set the initial conditions for the universe's large-scale structure. The implications of cosmic inflation are profound. If the universe expanded so rapidly in its early moments, could this process continue in other parts of the universe, even today? Some theories suggest that this inflationary process could still be happening, creating pocket universes within a larger multiverse, where each bubble could evolve with its own set of physical laws. Inflation challenges our understanding of time and space, suggesting that our universe may not be the only one to exist. The idea of a multiverse, an infinite number of universes, each with different properties, was made more plausible by the theory of inflation. But what does this mean for the future of cosmology? Could we one day discover a way to probe these other universes, or are we limited to understanding only our own cosmic bubble? While the theory of cosmic inflation offers exciting insights into the origin of our universe, it also raises questions about the ultimate fate of the cosmos. If inflation can create new universes, what is the eventual outcome for our own? Will the universe continue expanding indefinitely, or will it one day contract? To understand this, we must delve into the possibility of the Big Crunch, a scenario where the universe's expansion could reverse, leading to a dramatic collapse. What if everything we know, the stars, the galaxies, even the very fabric of space itself, was one day destined to collapse back into a singularity, a point of infinite density? The Big Crunch is one of the most dramatic theories about the fate of the universe, proposing that after billions of years of expansion, the universe might eventually stop growing and start contracting. As galaxies, stars, and all of existence begin to collapse inward, the universe could reach an end that mirrors its beginning, a fiery and dense singularity. But is this the inevitable conclusion of the cosmos, or is there another fate awaiting the universe? The Big Crunch is a concept rooted in the laws of gravity and the expansion of the universe. Since the Big Bang, the universe has been expanding, with galaxies moving farther and farther apart. This expansion is driven by the initial energy released during the Big Bang, and for a long time, it seemed that this momentum would continue indefinitely. However, the Big Crunch theory proposes that this expansion could eventually slow down and reverse if the gravitational pull of all the matter in the universe is strong enough to overcome the force driving the expansion. If gravity outweighs the forces causing expansion, the universe would begin to contract, with galaxies and stars slowly drawing closer together. Over billions of years, this process would accelerate, leading all of matter to collapse inward into an ever-dense singularity, much like the conditions that existed at the time of the Big Bang. In this scenario, time and space would cease to behave as we know them, and the universe would come to a fiery and violent end. The idea of the Big Crunch raises profound and unsettling questions. If the universe is fated to collapse back in on itself, does this imply that the universe is cyclical, with each expansion followed by a contraction, leading to an endless cycle of birth and destruction? If so, what is the purpose of this cycle? And how might life, as we know it, fit into such a grand, infinite process? Could the Big Crunch be just one chapter in a long history of universal rebirths? Furthermore, if the universe does eventually collapse, what will happen to the fundamental forces of nature, gravity, electromagnetism, and nuclear forces when all matter is drawn into a single point? Would time itself cease to exist? And would the laws of physics as we understand them break down? The Big Crunch presents a scenario that is almost beyond our comprehension, a complete reversal of everything we experience in the universe today. However, the Big Crunch is not the only possible fate for the universe. As we've seen, the universe's expansion continues to accelerate, suggesting that a more dramatic end might await us. The key, Big Freeze. In this scenario, the universe keeps expanding forever, growing colder and darker until all stars burn out. To explore this possibility, we must look at the long-term future of the universe and how its constant expansion could lead to an ever-cooling, ever-darker cosmos. What if, instead of a dramatic collapse, the universe simply stretches on forever, growing ever colder and more desolate? Imagine a universe where stars burn out one by one, galaxies drift farther apart, and the cosmos becomes a vast frozen expanse. This is the theory of the Big Freeze. a chilling and seemingly inevitable end to the universe in which it continues to expand endlessly. But in doing so, it gradually reaches a state of eternal darkness and cold. Unlike the violent Big Crunch, the Big Freeze would be a slow, gradual death, a universe where all forms of life and energy eventually fade away, leaving only emptiness. But how could this happen? And what would it mean for the future of everything we know? The Big Freeze is predicated on the current observation that the universe's expansion is accelerating. This was first discovered in the late 1990s, when astronomers noted that distant galaxies were moving away from us faster than expected, suggesting the presence of a mysterious force called dark energy. Dark energy is believed to be driving the accelerated expansion of the universe, pushing galaxies farther apart at an ever-increasing rate. If this expansion continues unchecked, galaxies will eventually be so far apart that the space between them becomes too vast for any form of interaction. Stars, too, will run out of fuel. Our sun, for instance, will eventually exhaust its hydrogen fuel and expand into a red giant. But long before this happens, the expansion of the universe will make the distances between stars so great that new stars will no longer form. As stars die and no new ones are born, the universe will grow darker, colder, and quieter over billions of years. The cosmic microwave background radiation, the faint glow left over from the Big Bang, will eventually fade, leaving a completely cold and dark universe. The Big Freeze paints a bleak picture for the long-term future of the universe. As stars die and galaxies drift apart, life, at least life as we know it, would be impossible to sustain. Without the energy provided by stars, and with the temperature dropping toward absolute zero, the conditions necessary for life to survive would no longer exist. This concept raises profound questions about the nature of existence. If the universe is destined to grow cold and dark, what, if anything, is the ultimate purpose of all that has happened up to this point? Could life, intelligence, or consciousness persist in such an inhospitable environment? Or would they eventually succumb to the inevitable march toward entropy? The Big Freeze is a theory that forces us to confront the ultimate fate of everything, an eternity of darkness, where the very fabric of the universe becomes so stretched out and isolated that time itself would seem to lose all meaning. While the Big Freeze presents a rather grim outlook, it also leads us to ponder the broader cosmic question of the universe's structure. If the universe is expanding indefinitely, what lies beyond the farthest reaches of space that we can observe? To understand this, we must delve into the theory of the multiverse, where the universe we know may just be one of countless others. What if the universe we know, the one with its stars, galaxies, and laws of physics, is only one of countless others, each with its own unique characteristics, laws, and perhaps even versions of ourselves? This mind-bending idea is at the heart of our multiverse theory, which suggests that our universe is just one of many, perhaps infinite universes that exist in parallel. These universes may coexist in ways we can't perceive, with each one having its own distinct set of physical laws and properties. The very thought of an infinite number of realities raises fascinating, yet unsettling questions about the nature of existence, free will, and our place in the cosmos. Could we truly be just one universe among an infinite number? Or is our reality more unique than we can imagine? Multiverse theory emerges from several areas of theoretical physics, particularly from the study of quantum mechanics and cosmic inflation. According to inflationary theory, the rapid expansion of the universe in its early moments could have caused regions of space-time to inflate at different rates. This could have led to the creation of multiple bubbles, each one expanding into its own universe with its own distinct properties. These bubbles may exist independently of one another, with no way of interacting or even knowing of each other's existence. Additionally, quantum mechanics introduces the idea that every decision, every possibility, could create a branching universe where different outcomes occur in different realities. In this version of the multiverse, every possible event that could happen does happen, but in different parallel universes. Thus, for every choice we make, an alternate universe is created where a different outcome unfolds. This idea, while still speculative, has been proposed as a way to understand the infinite number of potential outcomes in quantum mechanics. The implications of multiverse theory are staggering. If our universe is just one in an endless array of possibilities, then our reality, our very existence, might not be as unique as we believe. Could there be other versions of ourselves living different lives in parallel universes? What would it mean for the concept of free will if every possible choice we make creates an alternate reality? In the context of cosmology, the idea of multiple universes challenges the notion of a single finite universe with a beginning and an end. If there are infinite universes, each with different laws of physics, could some of these universes harbor life forms that are completely beyond our comprehension, with rules of nature that we can't even imagine? Perhaps in one universe, time moves backward. In another, gravity works differently, or the speed of light is not a constant. The multiverse offers a radical expansion of the possibilities for what could exist, suggesting that the scope of reality is far greater than our minds can grasp. As we grapple with the concept of the multiverse, we are faced with profound questions about the nature of existence itself. If there are countless universes, what does it mean for our own? Could our universe be one of many born from a higher-level cosmic process? To explore these mysteries further, we must consider the possibility of a whole cosmic purpose. The idea that the universe, and perhaps even the multiverse, has an underlying meaning or direction that we are only beginning to understand. Is the universe simply a vast, random collection of stars, galaxies, and particles? Or could there be a deeper, more profound reason behind its existence? The idea of cosmic purpose invites us to think beyond the physical processes of the universe and consider whether the cosmos itself has a goal, a meaning, or a guiding principle. For millennia, humanity has searched for purpose, both on an individual level and in the larger cosmic sense. As we peer deeper into the universe and uncover its mysteries, we must ask, are we merely products of chance in an indifferent, purposeless universe? Or are we part of a grand design that has yet to be fully understood? The concept of cosmic purpose suggests that the universe may not be the result of random events or mere mechanical processes, but could have an inherent direction or intention. This idea doesn't necessarily align with traditional religious views of a purposeful creator, but rather proposes that the universe itself might have an underlying order, perhaps guided by the laws of physics, mathematics, or some other unknown force. In a scientific context, some thinkers propose that the evolution of the universe, from the Big Bang to the formation of galaxies, stars, and planets, could be viewed as a kind of natural progression toward complexity, order, and consciousness. For instance, the development of life on Earth might be seen as an inevitable outcome of the laws of physics and chemistry, or even as a necessary step in the unfolding of a universe that, over time, gives rise to intelligent beings capable of contemplating their own existence. Some physicists and cosmologists have posited that the very structure of the universe, its finely tuned constants, the way matter and energy behave, and the emergence of life could point to a deeper, yet to be understood purpose. For example, the anthropic principle suggests that the universe's physical properties are remarkably well suited for life, and this fine-tuning might imply that the universe was somehow designed to support life. While some reject this as a coincidence or the result of selection bias, we only observe the universe because it allows for life. Others see it as evidence that the universe might have a deeper cosmic purpose. If the universe has a purpose, what does it mean for us as human beings? If we are part of a cosmic design, are we merely following a predetermined path, or do we have free will to shape our future? This question is particularly pressing when we consider our place in the universe. Could our actions, our search for knowledge, our ability to reflect on existence be part of a larger plan, one that transcends our understanding of time, space, and even life itself? Cosmic purpose also raises the possibility that the universe is not just a vast, indifferent expanse, but a dynamic system with meaning. This might challenge the notion of a random, mechanistic universe and encourage us to consider the universe as something more interconnected, perhaps even conscious of its own existence. As we reflect on the idea of cosmic purpose, we are led to consider the scale of the universe, its intricate design, and whether the forces that guide it might have a deeper connection to us. But what if the universe's purpose extends beyond what we can observe? Perhaps there are hidden dimensions, unseen forces, or cosmic truths that we are only beginning to understand. To explore this, we must turn our attention to the cosmic scale. Considering how the immense size and structure of the universe shape not only our understanding of space but also our place in it. When we gaze up at the night sky, the stars seem like distant, shimmering points of light, scattered across the vast, dark expanse. But what if we told you that these stars are not just dots, but massive suns, some far larger than our own? The scale of the cosmos is so staggeringly immense that it almost defies human comprehension. The more we learn about the universe, the more we realize just how small we are in the grand scheme of things. Our solar system, our galaxy, and even our entire observable universe are all but tiny specks in an unthinkable expanse. How do we even begin to grasp the infinite scale of the cosmos? And what does it mean for our understanding of space, time, and existence? The scale of the universe is mind-boggling. Our solar system is just a small part of the Milky Way galaxy, which is itself a part of the even larger cosmic structure known as the universe. The Milky Way contains over 100 billion stars, many of which have their own planetary systems, potentially harboring life. And yet, the Milky Way is just one of at least 100 billion galaxies in the observable universe. Each of these galaxies contains countless stars, planets, and other cosmic objects, some of which are billions of light years away from us. The sheer size of the universe is difficult to fathom. For example, light from the nearest star, Proxima Centauri, takes over 4 years to reach us. Even with the fastest spacecraft ever built, it would take tens of thousands of years to reach just the nearest stars. And yet, the observable universe itself has a radius of about 46.5 billion light-years, meaning that what we can observe is only a small fraction of the whole universe. Beyond that boundary, there may be even more galaxies, stars, and cosmic structures that we simply cannot see or detect. This vastness forces us to confront the scale of time itself. The universe is not static. It is constantly evolving. Galaxies collide, stars are born and die, and planets form and fade. The entire universe is in motion, with everything from stars to galaxies expanding away from each other at speeds that stretch the very fabric of space-time. And yet, this expansion is not something we can directly observe in our everyday lives, as it occurs on a scale far beyond the reach of human experience. The immense scale of the universe challenges our sense of perspective. If the universe is so vast, what does that say about our place in it? Are we simply insignificant specks in an incomprehensibly large cosmos? Or does the very fact that we are here, able to reflect on the nature of the universe, give our existence meaning? The scale of the universe invites existential questions about the purpose of life, the nature of consciousness, and our connection to the cosmos. It also raises the question of what other forms of life or intelligence might exist in the vast reaches of space. If the universe is infinite, could there be other civilizations out there, perhaps even more advanced than ours, living on distant planets in far-flung galaxies? What might they know about the universe that we have yet to discover? While the scale of the cosmos is humbling, it also opens up new possibilities for understanding the universe. If the universe is so vast, how do we make sense of its origin, its purpose, and its future? To explore these questions further, we must look at the process of cosmic evolution. The way the universe has changed over time, and the role that life and intelligence might play in its ongoing story. Just as living organisms are born, grow, and eventually die, could the universe itself follow a similar life cycle? The idea of cosmic evolution. proposes that the universe has undergone a series of changes since its inception, evolving in ways that are still unfolding today. From the explosive beginning of the Big Bang to the ongoing expansion of galaxies, the universe is not a static entity. It is constantly evolving, changing in response to the forces at work within it. This concept not only challenges our understanding of the universe's past, but also invites us to consider its future. Could the universe have a natural lifespan, undergoing cycles of birth, growth, and eventual death? And if so, what role do we play in this grand narrative? Cosmic evolution refers to the continuous process of change that the universe has undergone since the Big Bang. In the earliest moments, the universe was hot, dense, and filled with radiation. As it expanded, it cooled, allowing for the formation of atoms, which eventually coalesced into the first stars and galaxies. Over billions of years, these stars and galaxies continue to evolve, giving rise to the complex structures and systems we observe today. The process of stellar evolution, for example, leads to the birth and death of stars, with massive stars ending their lives in supernovae, creating the elements that make up planets, including Earth. The galaxies themselves are not static, but instead continue to merge, grow, and evolve, forming clusters and superclusters of galaxies. Even our own galaxy, the Milky Way, is in the midst of a slow collision with the Andromeda Galaxy, an event that will reshape both galaxies over billions of years. On a larger scale, cosmic evolution also refers to the expansion of the universe itself. Since the Big Bang, the universe has been stretching, with galaxies moving farther apart. This expansion is not just a simple stretching of space. It is the underlying force that has shaped the entire structure of the universe, influencing the formation of galaxies, stars, and planetary systems. In fact, the very structure of the universe, the distribution of galaxies, dark matter, and cosmic voids, is the result of cosmic evolution, shaped by the gravitational forces at play. The concept of cosmic evolution challenges the idea that the universe is a finished product, something that has simply existed as it is for eternity. Instead, it suggests that the universe is in a constant state of flux, driven by the same forces that govern everything within it. If the universe is evolving, does that mean it will eventually reach a natural endpoint, much like the life cycle of an organism? Some theories propose that the universe could one day reach a state of maximum entropy, where all energy is evenly distributed and no further work can be done. This would represent the ultimate death of the universe, a point beyond which no change or growth is possible. But even in this scenario, cosmic evolution may not be over. Could the universe be reborn in some way, perhaps through a process akin to a big bounce, where the universe collapses in on itself, only to be reborn in a new cycle of expansion? These possibilities raise profound questions about the nature of time, existence, and the future. If the universe is constantly evolving, what does that mean for our understanding of its origins and its destiny? How do we, as sentient beings, fit into this ever-changing cosmic narrative? Are we simply brief flashes of life in the vast expanse of time, or do we have a larger role to play in the ongoing evolution of the cosmos? As we consider the long-term evolution of the universe, we are forced to confront not only its potential end, but also the very fabric of its existence. How do we understand the forces that shape the universe on such an immense scale? To answer this, we must explore the ultimate question: what governs the behavior of the universe itself? To understand the forces of cosmic evolution, we must turn to the search for a unified field theory. The grand theory that could unite all of the universe's forces under one elegant framework. As we peer deeper into the cosmos, one of the most striking aspects of the universe is how perfectly it seems to support life. From the stability of the sun to the precise conditions that make Earth habitable, everything seems finely tuned for the existence of life. But why should this be the case? Is it just an incredible coincidence, or is there something more to it? The anthropic principle offers one possible answer to this question. It suggests that the universe appears to be specially designed to support life, because if it weren't, we wouldn't be here to observe it. This intriguing principle challenges our understanding of the universe's purpose, suggesting that our existence could be tied to the very structure of the cosmos itself. But does this imply a purposeful design, or is there another explanation? The anthropic principle stems from the observation that certain physical constants in the universe are precisely tuned to allow life to exist. These constants include factors such as the strength of gravity, the electromagnetic force, and the mass of subatomic particles. If any of these values were even slightly different, life as we know it would be impossible. For example, if the force of gravity were slightly stronger or weaker, stars like our Sun would either collapse or burn out too quickly to support life on Earth. Similarly, the balance between electromagnetic forces and gravity governs the stability of atoms and molecules, which are the building blocks of life. The principle comes in several forms, ranging from the weak anthropic principle to the strong anthropic principle. The weak version simply states that the universe must have the properties necessary for life, because life exists to observe it. It's a tautological argument. We observe the universe to be fine-tuned because if it weren't, we wouldn't be here to notice it. The strong version, however, suggests that the universe is fine-tuned for life in such a way that life is an inherent outcome of the laws of physics themselves, implying that the universe was somehow designed or set up with life in mind. The anthropic principle raises fascinating and sometimes unsettling questions. If the universe is so precisely tuned for life, could it be evidence of a grand design or an intelligent creator? Some see this as supporting the idea of a purposeful, intentional universe, while others argue that it is simply a product of statistical necessity. If there are countless other universes, each with different physical laws, then it's not surprising that one of them would have the right conditions for life to emerge. This view suggests that our universe is just one of many in a vast multiverse, where different combinations of physical constants result in different outcomes. In such a framework, our universe's ability to support life is not a miracle, but a statistical likelihood within a much larger ensemble of possibilities. Yet, the anthropic principle also forces us to confront our own significance in the universe. If life is such a rare and remarkable occurrence, does that make our existence uniquely important? Or are we simply one small, fleeting episode in an otherwise indifferent cosmos? The fine-tuning of the universe invites us to consider whether there is a deeper purpose to the cosmos, or whether we are simply lucky enough to live in a universe where the conditions for life happen to exist. While the anthropic principle raises profound questions about the nature of life and the universe's purpose, it also leads us to contemplate our role in the broader cosmic picture. If the universe is so finely tuned, then what does it mean for the future of life and intelligence in the cosmos? Perhaps, as we search for meaning, we must explore the very forces that govern the universe's behavior. To do so, we must turn our attention to the possibility of a B-unified field theory, the ultimate explanation for how the universe's fundamental forces work together, offering a glimpse into the deeper truths of reality itself. What if everything we experience, our world, our memories, even the stars in the night sky, were nothing more than a sophisticated simulation, a creation of an advanced civilization? The simulation hypothesis proposes that our reality might be a computer-generated simulation created by beings far more advanced than us. This idea, though seemingly straight out of science fiction, has gained traction among some leading thinkers in philosophy, physics, and technology. If the simulation hypothesis is true, it would radically alter our understanding of existence, consciousness, and the nature of the universe itself. Could we be living in a simulation? And if so, what does that mean for our perception of reality? The simulation hypothesis was popularized by philosopher Nick Bostrom in 2003, who argued that it is possible that an advanced civilization might develop the technology to create highly realistic simulations of entire universes, complete with conscious beings. These simulated beings would be unaware that their reality is artificial, experiencing it as if it were genuine. According to Bostrom, there are three possibilities. Either advanced civilizations never develop the technology to run such simulations, they do but choose not to create them, or we are already living in one. The latter scenario suggests that it is more likely than not that we are living in a simulated reality, considering the potential for countless simulations to exist in an advanced civilization. This idea hinges on the rapid progress of computational technology. As our own computing power increases and we develop more advanced artificial intelligence, we are moving closer to the point where we could simulate entire worlds. If we were able to create simulations indistinguishable from reality, why wouldn't a more advanced civilization have already done so? These simulations could involve not just simple environments but entire universes, with simulated consciousnesses experiencing life just as we do. If the simulation hypothesis holds any truth, the implications are profound. For one, it calls into question the very nature of existence. If we are living in a simulation, what does that say about our minds, our free will, and our purpose? Are we merely characters in a game, controlled by the whims of a creator, or do we possess true autonomy? Could our thoughts and actions simply be predetermined by the programming of the simulation? Or is there room for free will within the bounds of the simulated reality? These questions challenge our understanding of consciousness, suggesting that it might not be tied to a biological brain, but could instead be a product of sophisticated computational systems. Furthermore, the discovery of living in a simulation could have significant philosophical and ethical ramifications. Would the knowledge that we are in a simulation change the way we view life, morality, and the universe? Would it diminish the meaning of our existence? Or would it invite us to redefine purpose within the context of a simulated world? Some argue that if we are in a simulation, the creators of that simulation might have designed us with a specific purpose or goal in mind, perhaps as an experiment or a means of observing the development of intelligence. Others worry that the realization could lead to existential despair as we confront the possibility that our lives are nothing more than a program running on a far-off computer. While the simulation hypothesis raises fundamental questions about the nature of reality and existence, it also invites us to consider the ultimate nature of the universe itself. If we are living in a simulation, could the real universe exist outside of our understanding? To explore these mysteries further, we must consider the possibility of a unified field theory, a framework that could offer deeper insights into how the universe and potentially the simulations within it operate on a fundamental level. For centuries, scientists and philosophers have searched for a single unified theory that can explain all the forces of nature. Could there be a single elegant framework that ties together gravity, electromagnetism, and the fundamental forces that govern the universe? The unified field theory is the theoretical search for a comprehensive explanation of the universe where all the forces and particles are connected in one unified framework. It is often referred to as the theory of everything, as it aims to provide a single set of equations that can describe everything in the cosmos, from the smallest particles in quantum mechanics to the vast scale of galaxies and the structure of space-time itself. But is this theory just a dream, or could it be the key to understanding the true nature of the universe? The quest for a unified field theory dates back to Albert Einstein, who spent much of his later life attempting to unify the two great theories of physics: general relativity, which describes gravity on large scales, and electromagnetism, which governs the behavior of electric and magnetic fields. Although Einstein was unable to complete his work, his ideas paved the way for modern physicists to continue the search. Today, the concept of a unified field theory seeks to bring together the four known fundamental forces of nature: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Gravity, which governs the motion of planets and the structure of the cosmos, is described by Einstein's theory of general relativity. Electromagnetism governs the behavior of charged particles and is described by quantum field theory. The weak and strong nuclear forces are responsible for the interactions between subatomic particles, such as those in atomic nuclei. These forces, though well understood in isolation, are described by separate theories that do not fit together cohesively. The goal of the unified field theory is to find a single framework that unites these forces into one theory, explaining how they interact and why they behave the way they do. One promising approach to a unified field theory is string theory, which posits that the fundamental particles of nature are not point-like objects, but rather tiny, vibrating strings. These strings could, in theory, explain all the forces of nature by unifying gravity and quantum mechanics into a single framework. While string theory has not yet been proven, it has inspired new ways of thinking about the fundamental structure of reality. The discovery of a unified field theory would be a monumental breakthrough in science. It would not only allow us to explain the workings of the universe from the smallest particles to the largest structures, but it could also lead to new technologies and innovations that we cannot yet imagine. For example, a deeper understanding of the forces of nature could provide insights into the nature of dark matter and dark energy, two of the most mysterious and elusive components of the universe. A unified theory might also allow us to better understand the nature of black holes, the behavior of space-time near singularities, and the potential for manipulating space and time itself. However, the implications of such a discovery are not only scientific, but philosophical. A unified field theory could provide a deeper understanding of the nature of reality itself, offering answers to some of the most profound questions in existence. What is the ultimate nature of the universe? Is the universe deterministic, or is there room for free will within a unified framework? Could the discovery of this theory point to an even deeper layer of reality, one that we have yet to comprehend? While the search for a unified field theory represents the pinnacle of scientific inquiry, it also suggests that the universe may hold secrets far beyond our current understanding. What if this theory is just the beginning of a greater journey, one that takes us beyond the limits of space and time? To explore what might lie beyond, we must consider the possibility of cosmic purpose. The idea that the universe, in all its complexity, might be guiding us toward an ultimate goal. What role does the search for understanding play in this grand cosmic narrative?